Okay, guys, so I realized if I did make this recording, I can't find it. So I'll have posted up this PowerPoint file so that you can go along and take notes, and follow this, and I'm going to publish it in sections. And it's sort of, there's no one way of doing this, but I can at least show you I picked this kind of geometry because it combines a couple of other simple ones, but it uses techniques you would always use with simplifications for due to the symmetries here. So our charge in question is a line charge, and it's on a circle, and the radius of that circle, if you think of this imaginary line, a circle drawn, it's got a radius a, and it has a total length of pi over 2, which is 90 degrees. And so from here to here is an angle of pi over 2, sweeps out. And we'll talk about that in a minute. And we want to know, what is the electric field at point P? So that's our point of interest. So, we can't just look up a formula for that. There is no formula for that. But we do know a very simple formula for the field of a point charge. And I think I've mentioned it. Integration is an infinite sum of infinitely small things. That's when that dx, you let dx go to 0. So what we could do, we can imagine now, oh, wait a minute, a point charge, or for example, a point charge is infinitely small. So what we can do is we can say, okay, let's just pick a piece of the charge we're given. We're going to say we got this little bit here, dq, and I drew it as a square, and it's bigger than what it is. But it's just the idea that you could have a block of charge, right? So we want to pick a little dq in there, some small bit of charge. And in this case, if we do that, then this thing is going to behave almost like a point charge. So now we have our dq, and we say dq is small. And just for imagination's sake, for the moment, it's basically almost a point charge. And what we're going to do is we can imagine actually that to figure out what is the field at P, we can actually say, let's just divide this up into a bunch of dq's, right? So we could divide into many dq's, and then we can use the formula we know, and we just say that's dq now, because that's the size of the charge, and the k, and we have the r squared, and we're kind of lucky here in this case because r is going to be constant, but maybe not. And what we'll do is, for every little dq, we'll calculate the E field, and the principle of linear superposition says we can add them up, right? But of course, remember, it's almost a point charge, right? So, okay, how many DQs? Well, let's make them small. And so then they'll behave more like a point charge, right? So then we reduce error. Trouble is then we're going to be punching our calculators quite a bit, right? So that means, but the implication is then it takes a long time and it's boring. But what we do know is that with calculus, we can make an infinite sum of infinitely small things. So if we let dq become infinitely small, Ly, then it will be a point charge. So then if we sum them up, we'll get the exact right field. Of course, that's not physically possible for a human being to do, but that's where the integration comes in. Now, of course, the problem is that this is all well and good, but we also know it's a little bit more complicated than that. And yeah, there's going to be a k. There's going to be 1 over r squared. And, okay, now what would be the limits of integration, huh? So this is, so far, we just have a concept. So, gosh, now what can we do? So what we have to do is we have to figure out, we have to make q dq into something that we can integrate. I'm looking over to this PDF of my notes. Okay. So what we're going to do is, let's jump ahead. Okay, so first of all, we have a total charge Q, capital Q. And in this case, we might get told this, but we're going to assume that it's what we call a line charge. So that means that all the charges are sort of in this imaginary line. And so as opposed to if it was like something like thick thing like this, then there would be, we'd have to take into account that there would be a difference in R from the outside to the inside. R outside, R inside. And we don't want to deal with that. And unless the problem says differently, we're allowed to do whatever the heck we please. So a line charge is characterized by the number of coulombs per length, and unit length, of course, per meter. And then when we know the length, we can multiply this by the length, and we can find out how much charge we have, right? So the symbol that's generally used for this is lambda for the charge per unit length. So, okay, we need to know what is the length of our charge. Oh, what's the timer going? I'm going to look at my record. I don't like these going more than, so about 10 minutes. Okay. The length of our charge, well, we know that we have a radius here called A. And we also know something about radians. So we know, for example, there's 2 pi r radians in, excuse me, 2 pi radians in a circle, and then the circumference of a circle is 2 pi r, which is a length, right? Okay, so we have an arc, instead of 2 pi, we have pi over 2. So we can see that the length of our charge is equal to pi over 2 times A. Oh yeah, lambda is defined by total charge over length. I forgot to write that. So in our case, lambda is going to equal capital Q divided by pi over 2 times, give me a minute, times A. So we can just simplify it a little bit. 2q over pi a. Now, we also need to know then, we have to make an expression then for how much charge is in dq. And then another thing we'd like to have is we need a convenient coordinate, because we're not going to integrate x and y here, and we might have to, but in this case we know that we have a constant radius vector. So what we're going to do then, we're going to define ourselves a, well, first of all, let's draw a couple lines here. Oops. And notice how those lines go from the center, and they go to either side of our dq. There's our radius again. So we're going to define a variable. We're going to call it alpha, an angle. And we're going to say that alpha, this is the positive direction. This is alpha equals 0, for example, alpha equal pi over 2, alpha equal pi, etc. And then notice that I can make these two radius vectors, and then we can see that there's an angle inside of there, and we're going to call that d alpha. So that means then that what we need for dq to figure out how much charge is, we need to know what length is within dq, and we're just going to go back to this sort of 2 pi r kind of thing, but in this case it's going to be r, the radius, times d alpha. So we have a radius times an angle, and it's going to tell us how much, if we put a in meters, that's going to tell us how many meters long dq is, the length of dq. So if we take the length of dq and multiply it by the charge per unit length, so that means then a times d alpha, and we multiply it by 2q over pi a, this is going to equal how much charge we have, because we're going to get meters times coulombs times over meters, and we end up with coulombs. And just to make our lives a little bit easier, instead of writing out that big mess, we'll just go back to saying that, well, let me pause this for a moment. Yeah. And so at the end of the day, we're going to have lambda, we're going to have A lambda d alpha. So it's much easier to write. We do know, I was a little worried about that the A's at the end of the day, the A's will cancel at some point, but we still have to keep the A right there. Okay, so it's time to stop this video because it's over 15 minutes, and we will start making a new one with the next slide.